What if everything you thought was ordinary, your phone, your GPS, your doctor's scanner, was powered by the strangest science in the universe? A science where particles exist in two places at once, where cause and effect blur, and where just observing something changes its reality. That science is quantum physics. And it's not just locked away in laboratories or theoretical papers. It's inside your life, right now, shaping everything you do. Quantum physics isn't science fiction. It's not a fantasy or a theory about distant galaxies. It's the foundation of the most advanced technology humanity has ever created. From the moment you wake up and check your phone to the satellites guiding your GPS, quantum mechanics is at work. But to understand why, we have to go back to the roots, what quantum physics really is. At its core, quantum physics is the study of the smallest building blocks of reality. Not atoms, but what's inside atoms, electrons, photons, quarks, the stuff that makes up all matter and energy. In the 20th century, scientists realized that the classical laws of physics, like Newton's laws, break down when you zoom in far enough. On this tiny scale, particles behave in ways that seem impossible. A particle can act like a wave. An electron can exist in multiple places at once until it's measured. Two particles can become entangled, meaning that measuring one instantly affects the other, no matter how far apart they are. This isn't speculation, it's been tested, repeated, confirmed. And this bizarre behavior is not just a curiosity. It's usable, it's practical, and it's what makes your modern life possible. Let's start with something simple. You unlock your phone with facial recognition. The camera captures light, which is made of photons, quantum particles. The image sensors inside that camera rely on the photoelectric effect, a quantum principle discovered by Albert Einstein. He showed that light doesn't just behave like a wave, it behaves like a packet of energy. When those packets hit a material, they knock electrons loose. This is how light sensors and solar panels work. Your phone's camera wouldn't function without quantum mechanics. Now let's move deeper into the brain of your phone, the processor. Every chip inside your device is made of transistors. These are microscopic switches that turn on and off billions of times per second, forming the binary code of ones and zeros that powers everything from text messages to TikToks. But as we made transistors smaller, down to just a few nanometers, quantum effects started to appear. One of those effects is quantum tunneling. In classical physics, if there's a barrier in the way, a particle can't go through unless it has enough energy. But in the quantum world, particles don't follow those rules. Sometimes they tunnel through barriers as if by magic. It's not magic, of course, it's probability. At the quantum level, particles have a probability of being in more than one place at once. And that probability allows them to pass through walls that should stop them. This tunneling can cause problems in tiny circuits. Electrons leak where they're not supposed to. But it also opens the door to entirely new kinds of technology. Quantum computers. Quantum computers don't use bits like regular computers. They use qubits, quantum bits, that can be 0 and 1 at the same time, thanks to a phenomenon called superposition. That means they can process multiple possibilities simultaneously. In the future, quantum computers may solve problems that would take classical computers billions of years. But even today, quantum principles are already in your hands. Let's say you're using GPS to navigate. You type in your destination, and the map calculates your route in seconds. But did you know that GPS wouldn't work without Einstein and quantum physics? GPS satellites orbit Earth at high speeds and in weaker gravity. According to Einstein's theories of relativity, time ticks differently for them. Their clocks run faster than ours by about 38 microseconds per day. If that time difference weren't corrected, your GPS location would be off by several kilometers. To synchronize those atomic clocks, yes, actual atomic clocks in satellites, we rely on quantum mechanics. These clocks measure the frequency of light emitted by atoms jumping between energy levels, a purely quantum process. Without this precision, GPS would be useless. So every time you get directions, track your steps, or find the nearest coffee shop, you're depending on quantum timekeeping. And that's just the beginning. Lasers, which are used in barcode scanners, fiber optic communication, surgery, and even music concerts, are also rooted in quantum physics. The term laser stands for light amplification by stimulated emission of radiation. That process, stimulated emission, was predicted by quantum theory. In short, when an excited atom drops to a lower energy state, it releases a photon. That photon can trigger other excited atoms to do the same, producing a coherent beam of light. That's a laser. And lasers are in everything from your Blu-ray player to high-speed internet. Now consider medical imaging. MRI machines, magnetic resonance imaging, are one of the most powerful diagnostic tools in modern medicine. They don't use harmful radiation. Instead, they use quantum spin. Spin is a quantum property of particles like protons and electrons. It's not literal spinning, it's a type of intrinsic angular momentum. When you lie inside an MRI scanner, a strong magnetic field aligns the spins of hydrogen nuclei in your body. A radio frequency pulse then knocks those spins out of alignment. When the pulse stops, the nuclei realign and emit signals. Those signals are captured and transformed into images of your brain, muscles, or organs. That's quantum physics, mapping your insides non-invasively. Even the screen you're watching this video on might use quantum dots, tiny semiconductor particles that emit specific colors of light when stimulated. They're used in the most advanced display technologies to create richer, more accurate colors. Again, a product of quantum engineering. It may sound strange, but the more you look around, the more you realize quantum physics isn't some far-off theory. It's built into the fabric of your world. It doesn't just describe atoms, it shapes your devices. It powers your navigation. It reveals your body. It keeps time across the planet. And that's before we even get to what's coming next. Because the future of quantum physics isn't just about understanding, it's about harnessing. Quantum sensors that can detect brain activity with unprecedented detail. Quantum encryption that can't be hacked, ever. Quantum networks that transmit information instantaneously across cities, continents, maybe one day across the stars. And yet most of us never think about it. We live in a quantum world without realizing it. We build on principles we don't fully understand. We benefit from discoveries made by physicists who once thought they were studying pure theory. But here's the twist. The more we explore this strange and beautiful science, the more we realize that quantum physics isn't just behind the curtain, it is the curtain. It's not a layer on top of reality, it is reality. And you're part of it. Every breath you take, every tap on your screen, every atom in your body, all dancing to the rules of a universe that's not as solid or predictable as it seems. So the next time your phone loads a page, or your GPS finds your location, or a laser scans your ticket, remember this. You're not just using technology, you're using quantum physics. And it's not finished with us yet. We are standing at the edge of a revolution, not one of politics or economics, but of information itself. Quantum physics, once the playground of theoretical physicists, is now entering the world of technology in ways that could change everything we know about computing, communication, and security. Let's begin with the concept of the quantum computer. Traditional computers use bits. Each bit is either a 0 or a 1. Billions of these bits switch on and off to process information. It's powerful, but it's also limited. Quantum computers use qubits. And a qubit is not just a 0 or a 1. It can be both at the same time. This is called superposition. Imagine flipping a coin. In classical physics, it's either heads or tails. In quantum physics, until you observe it, it can be both simultaneously. A qubit is like that coin suspended in mid-air, existing in all possible outcomes until it's measured. Now scale that up. 2 qubits can exist in 4 states at once, 3 qubits in 8. With each additional qubit, the number of possible states doubles. That means a quantum computer with 300 qubits could represent more combinations than there are atoms in the observable universe. But it's not just about volume, it's about parallelism. A quantum computer can evaluate multiple solutions to a problem simultaneously. It's not just faster. It's fundamentally different. It doesn't follow the same rules as the computers we use today. And this opens the door to solving problems that were previously impossible. Take cryptography. Most digital security today relies on a principle called prime factorization. It's easy to multiply two big prime numbers together, but incredibly difficult to reverse the process. This asymmetry is the basis for RSA encryption, which protects everything from emails to bank accounts. For a classical computer, factoring a 300-digit number would take longer than the age of the universe. But a quantum computer could do it in seconds, using Shor's algorithm, a quantum algorithm specifically designed for this kind of task. That's not theoretical, it's real, and it's a warning. Quantum computing has the power to break today's encryption, but it also gives us tools to build something even stronger: quantum encryption. This is where things get even stranger. Quantum communication relies on a phenomenon called entanglement. When two particles are entangled, their states are linked instantly. Change one and the other responds, even if it's on the other side of the planet. It sounds like science fiction. It's not. In 2017, Chinese scientists used entangled photons to send encrypted messages between ground stations over 1,100 kilometers apart via satellite. The communication was secure not because of stronger math, but because of physics itself. Here's how it works. If someone tries to intercept the message, the act of measuring the photons alters them, due to a fundamental rule of quantum physics called the observer effect. You can't eavesdrop without leaving a trace. This is the foundation of quantum key distribution, or QKD. It's unhackable, not because it's hard to break, but because the laws of nature forbid it. Now imagine a future where your bank transactions, your health records, your national infrastructure, all are protected by quantum encryption. Not just safer, physically secure, but there's more. Quantum sensors are pushing the boundaries of what we can detect. These sensors use entangled particles or superposition to achieve sensitivities beyond classical limits. In medicine, quantum sensors could lead to brain imaging with incredible precision, detecting the tiniest magnetic fields generated by neural activity. This could revolutionize neuroscience, allowing us to observe thought in real time. In geology, quantum gravimeters can detect underground structures, useful for locating oil, gas, or even archaeological ruins without digging. In navigation, quantum accelerometers could replace GPS entirely. They measure changes in motion with such accuracy that a submarine or spacecraft could know exactly where it is without any external signals. This is not future fantasy. These technologies are being tested now. The quantum age is no longer just coming. It has begun. But with all this power comes a question: how do we control it? Quantum systems are fragile. Qubits are sensitive to noise, heat, interference. A stray vibration or magnetic fluctuation can cause decoherence, a collapse of the quantum state. That's why quantum computers require extreme conditions, temperatures near absolute zero, ultra-high vacuum chambers, and error correction algorithms more complex than anything used in classical systems. Yet progress is being made. Companies like IBM, Google, and startups like Rigetti are building ever larger quantum processors. Google made headlines by achieving quantum supremacy, performing a calculation in 200 seconds that would take the most powerful supercomputer thousands of years. That specific task wasn't useful, but it proved something big. Quantum advantage is real, and it's coming faster than we thought. But quantum technology isn't just about computing. It challenges the very nature of reality. Physicists still debate what quantum mechanics really means. Does the universe split into multiple versions every time a particle is measured? Is consciousness involved in collapsing wave functions? Is time truly linear or just an emergent property of entangled systems? These questions aren't abstract philosophy. They're being tested with increasingly advanced experiments that blur the line between physics and metaphysics. And here's what's even more fascinating. Everything quantum technology is achieving, every breakthrough, every invention, is based on rules we don't fully understand. We know the math works. We know the predictions are accurate. But we don't know why the universe is this way. It's as if we're using tools from a language we haven't fully learned, like speaking fluently before we understand the grammar. And yet the results are undeniable. Quantum mechanics powers lasers, semiconductors, medical scanners, atomic clocks, superconductors, LEDs, and even the click of a button on your mouse. It underpins our digital age, even as it opens the door to the next one. The age of quantum connection. A world where information isn't just sent, it's entangled. Where computation isn't binary, it's exponential. Where encryption isn't secure by trust, but by physics. We are about to enter a world where reality is no longer fixed, but fluid. Where certainty gives way to probability. Where technology operates not just by harnessing matter, but by shaping possibility. And the question isn't whether we're ready. It's whether we're even capable of understanding what we've built. Because the quantum world isn't waiting, it's already here. Quantum mechanics doesn't just describe the invisible, it reshapes how we see everything. From the way we power cities, to how we encrypt data, to the tools that diagnose our illnesses, the quantum world is no longer confined to labs and equations. It's embedded in our lives, guiding the evolution of science, technology, and even thought itself. And yet, for all we know, we've only scratched the surface. Quantum theory remains incomplete. Its deepest mysteries, like the role of consciousness, the nature of time, or the reason behind wave function collapse, are still unsolved. We don't just need better tools, we need better questions. Because in the end, quantum mechanics isn't just about particles and probabilities. It's about possibility. It teaches us that reality is not fixed. That certainty is an illusion. That even the smallest pieces of the universe contain infinite outcomes, waiting to be observed, waiting to become real. And maybe that's the lesson, that we too are part of this unfolding equation. Not just observers, but participants. Not just thinkers, but experiments in progress. The quantum world isn't somewhere far away. It's right here, and it's just getting started.